phone.
Game, you know,
Candy Crush Saga. You're not one to judge, okay? Go back to your Banfield or whatever it is you were doing.
In cricket, you need, like a strength to hit a hard ball out of the stadium.
Look, don't try to convince him, alright? He has bad taste.
Yeah, but if the ball doesn't go out and it goes towards somebody's face.
There's a batsman who can throw the ball outside the stadium.
No, I'm saying if he doesn't, like the safety risk, if he hits somebody else's face or the audience watching, what happens?
In the stadium, when they're watching, it catches maybe one or few times it hits, but normally people are watching in the stadium the ball, where it's ball going. They're not just doing their stuff.
Look, I wouldn't worry about it. How likely are you going to find yourself at a cricket match? What situation in your life will have you one day going, you know what, I never thought it, but I'm in a cricket match right now.
No, they used to play here,
not comparable.
They play with the tennis ball.
Yes, because if they should hit the ball, it could go to somebody's windscreen.
Yeah.
Do you even have a car here? Do you?
Or somebody's glasses, or somebody's face.
Now you need glasses, and I wouldn't worry about your face.
Your face can bounce the ball to that.
It's your brain what you need to worry about.
It's part of it.
Especially the maths physics part. You can damage the EAP and chemistry part, but leave the maths physics part intact, please. And the sci-fi part as well. Alright. So what we're looking at now, we're starting a new chapter.
Newton.
Yeah. Well, this is just the name of this lesson. This chapter is called Numerical Methods. Yeah, you see it there, Numerical Methods.
What
That's just the first topic in the chapter.
What does ODE mean?
We'll get to that when we get to do it.
The Newton law?
No.
Then why Newton?
Because Newton did many things.
I've been doing physics for 7 years and I cannot pronounce his name well, or spell it well.
Who?
Newton.
Oh dear, don't admit that in public, please. Yeah. So, this chapter, in fact, is a really important chapter, and it's more important nowadays than was in the past. But even though this chapter is more important nowadays, it was still important in the past. It's more important now because of computers. So this method is all about techniques to get to the answer. Let me explain with an example. So, for example, at the moment, if I give you a linear equation, you can solve it, right? And if I give you a quadratic equation, you can use the quadratic formula and you can solve it.
Maybe.
But no, I mean, you could use even if it was difficult, you could just use the formula. Yeah? But what's the deal with cubics? If I gave you a cubic, could you solve it?
Yes.
But with a condition.
Yes.
Which is what?
You have to use your calculator.
Yeah, but what?
Long division.
Yeah, but the condition is you must be able to find one of the roots before you can use the long division. And what do you require to be able to find the root? Well, it must be small. Easy to guess.
Few numbers like 0, -1, 1, +2, minus.
So what if the number was 1.5?
It's just guessing into the.
Yeah, so with Newton-Raphson, we're trying to find a better way than just blindly guessing. We'll still be guessing a root, but we have a process here, I'll show you, that will help you get towards the root without having to just blindly guess. So it's a very useful technique. So we'll take the proof, we'll use something like a graph like this. So for example, you imagine that you have a graph like this, and it looks like a quadratic, it has 2 roots. So let's pretend you guess here as x1. Now let's call this fx. Is this the root, x1?
No.
No. The root is over here, isn't it? So we guess x1, we put x1 into our formula, and we get y1. Will y1 be 0? No, it'll be far from it. It'll be here. This will be x1, y1. And how did we get y1? Yeah, so it's x1, fx1. Now that is definitely not the root. But here's the trick, the magic. If you draw a tangent line at this point and continue the tangent line down to the x-axis, this value here will be much closer to the true root than your first guess. So by following a tangent line downwards, we can improve our guess.
We can say it's less than or greater than.
No, we're just saying that if we could make a tangent line, we can zoom down to the x-axis and find a better estimate of the root.
And find linear roots.
A linear root, yes, exactly. So let's find this tangent line. So what is the equation of a tangent line? Y equals mx plus c. How do you find the m for a tangent line, semester 1?
So put the y2 minus y1.
Tangent line only has 1 point. The derivative at x1, that's the slope. How do you find the c?
Put the x and the y.
Which is right here, isn't it?
Yes.
So we can put this in, or do a different colour. You get fx1 equals f derivative x1, x1 plus c. So what does c equal? fx1 minus f derivative x1, x1. So I'll write it down here now. So we have y equals f derivative x1 x plus c, which is fx1 minus f derivative x1, x1. Now we don't want the tangent line. What do we really want? Yeah, where the tangent line crosses the axis. So let me call that point here x2. We make it 0. So we have 0 equals f derivative x1, x2, plus fx1 minus f derivative x1, x1. No, but it'll simplify now. So remember, we're looking for the x2. So I'll take the other two terms to the right. I think I made a sign mistake somewhere. Yes?
That x is meant to be x2 as well. One at the end.
Oh, sorry, I wrote x1, didn't I? No.
Because that's like a c.
Yeah, but the c is a constant, it doesn't change. Let me just double check back here. That's right. Hang on. That's right. So this fx1 equals, that's right. That's right. That's right. That's right. That's right. That's right. And we put in x2 here. No, this looks okay, I guess. Let's see what happens. So if I take the other terms to the right, I get f derivative x1, x1, minus fx1 equals f derivative x1, x2. Now what should I divide by? Because remember, I'm looking for x2. What should I divide by? The derivative. So I get, if I divide by the derivative, this cancels, this cancels, so we end up with x2 equals x1 minus fx1 over f derivative x1. Or if I write the x2 on the right, I can say it's like this. So what I'm saying is, previously when we tried to find the root of a cubic, we guessed 1. And then what's our next guess?
Like minus 1, 1.
No, if I start with try x equals 1, what would you try next?
2.
You could try 2. Whereas what this formula is saying, no, if you try x1 first, then you should try x2 next. Now I want to show you this in the graphing program because I think it'll help you visualize. So let's pick something, a quadratic that we know the answer to.
But it's not like if you tried 1, you're going to try like 2. You can go minus 1.
You can, but still my point is the same. Okay. Right, so we know that the roots are what?
1 and 1.
1 and minus 1. We definitely know that, but let's pretend we didn't know that.
Okay.
And let's pretend we tried 2 at the beginning. Will we get 0?
No.
No, because it's not a root. So if you put 2 into this, I'll expand it for you even. If you put 2 in here to our function, what will we get?
4. Minus 1 over 3.
Thank you.
Because that's
Yeah.
what it
So you see you get 3. Okay? Now what is this formula doing? It's making a tangent line at 2. So let me try and get the program to draw that if I can. No, it didn't work. Let me try this again. So it draws a tangent line at 2. And where does the tangent line cross the axis? About
1.3.
1.3. Is that closer to the true value than the original 2? Yeah, it is. So let's see. If we use the formula, what's the formula for x2? What do we need to know? Well, we need to know the derivative. So let's differentiate this. We get 2x. So what's the formula? It says x2 equals x1 minus fx1 over f derivative x1. Now what was my first guess? 2. And what is f of 2? We worked it out earlier. It was, no?
Minus 3.
Try again. 3. Now what's the derivative? 2x. So if I make x equal to 2, what's 2x? 4. Okay, so we get 1.25. So let me just write that down as an example. So for example, you have f of x equals x squared minus 1. And you guess, firstly, that x might be 2. So this formula says the next guess you should use should be 2 minus, now here on the top you would have 2 squared minus 1. And then what do you have on the bottom? What's the derivative here? What's the derivative?
2x.
2x. So on the bottom you would have 2 times 2. Because where x is 2. So this equals 1.25. Is that a better guess than 2? It is, because what's the true answer? Should be 1. Now this is the interesting part. We could use this formula again to draw another tangent line. So one sec, watch this now. If I draw another tangent line, but this time I draw it at 1.25, now look what's happened. Can you see that? I'll zoom in. Oops. Now look, that was my first tangent line, and then when I use the formula again to make another root from the next tangent line, look how close that is to 1. It's moving really close to the answer really Newton's formula, you could use it again and again many times. So you don't need to only use it twice. You could then use the answer the second time to make the third guess.
If our guess was like -2.
Yeah, we'll get to that in a second, some examples. So what you could now do is say, well, you can make it a sequence. The next guess is equal to the last guess minus not f xn over f derivative xn. This is the formula called Newton-Raphson's formula. It's a sequence, and the sequence moves to the root.
If you have n plus 2, what happens to the n?
What do you mean?
Like,
There isn't. No, what you're saying is the next guess. It's a recursive sequence from semester 1. The next guess equals the last guess minus this piece here, this term here. So this calculation here moves you closer to the answer. I'll show you in an example.
Yeah.
I think will be best.
Oh yeah.
So I need to pick something where the answer is obvious, so you can see that it's moving towards the answer. So for example, if I had a function like fx,
I finished your time.
oh, is it this thing?
Yes. Since you need one.
Oh, we'll do this one then, okay.
Not the one.
Did you have the formula?
Yeah.
And we'll start at a weird guess.
Yeah.
Yeah. So we have this formula down, Newton-Raphson, yeah? You have this? Okay. So let's pick something like simple like x squared minus 1. So what are the possible values for x? The solution could be 1 or minus 1. So let's pick something. Yes, what?
Oh yeah, it could be
Yeah?
x value, right?
Yeah, there's root. It's 1 or minus 1. These make zeros. Yes? Yep. So let's try some ridiculous guess. What would be like a terrible guess for the root?
3, 4,
No, terrible.
minus
10,
8,
15.
minus 8 over 5.
Let's try, okay, maybe the first root is 10,000.
Ah!
Don't go that far.
Why not? It's a terrible guess, isn't it? Now, what is the derivative here? We need to write down the derivative as well. What is it? 2x. Okay, so far okay? So Newton's law, Newton-Raphson's rule, says that x2 equals x1 minus fx1 over f derivative x1. So that will equal, now you know what, I find it's a little bit easier to work this part out before I put the numbers in, because we're going to have to put the numbers in many times. So I'll write Newton's law out like this. I'll write it out like this. Xn plus 1 equals xn minus fxn over f derivative xn. So xn plus 1 equals xn minus xn squared minus 1 over what? 2 xn. What type of formula is this? It's something that you've seen before. What's it called? It's recursive. Remember from semester 1. Alright, so we'll start with x1 equals 10,000.
X squared minus
Xn squared minus 1.
the square is on n or x?
No, the x.
Yes.
Why did you put n there?
Because it's xn. It's f of xn, not f of x. No, is it okay? I do worry sometimes. Is it okay? No, it's not okay. Tell me if it is or is not. You can be honest. Don't worry about KJ. Yeah, look. Look.
Yeah.
This is xn plus 1. Agreed?
Yeah.
And what's this one? xn. And this is f of xn. And what is f of x? X squared plus 1. So what is f of xn? Fine, x squared minus 1. So what is f of xn?
X squared and
xn squared minus 1 over 2xn. This is like what we did in functions as well. You know, f of x is blah, so f of y is the same thing, but y instead of x. So instead of x, I have xn. So instead of x, I have xn. Right. x1 equals 10,000.
Okay, so x2.
So x2 would equal 10,000 minus 10,000 squared minus 1 over 2 times 10,000, which equals 5,000. Now, how can I improve this?
Use the multiplier.
Yeah, so if I put 5,000 in here, I'll go straight to the answer, okay? If you put in 5,000, you'll get 2,500. What? This is recursive sequence. We did this in semester 1.
Just put the number in the formula.
Now, if I put 2,500 back in, so if I put that in here, I'll get 1,250. If I put 1,250 back in,
You forgot you made a project on recursive sequence. Read up
Mhm. Oh, I didn't forget that. You forgot that. So if I put 1,250 in, I got 625.
And how long?
Well, I started at a really bad guess, but in not too long, it starts to move in at the point. So after the 10th use of the formula, 11, now I'm starting to really get close to it now. Now we're getting really close. So after the 15th guess, I'm at 1.078. Then after the 16th guess, I'm at 1.003. And then at number 17, I'm at 1.000004, which is practically there.
You do it again.
If I do it again, yeah, the calculator rounds it to 1.
All again.
No, the calculator rounds it to 1. So if I did it again, it's still 1. It's reached its limit. Now think about this. This is quite amazing. Because if you were to guess and you start at 10,000, how many guesses would you need until you get to the answer? Well, if you start at 10,000 and the answer is 1, and you go 10,000, 9,999, 9,998, how long would that take? How many guesses? 10,000 guesses. How many did it take here? 18. So which is quicker, 18 or 10,000? 18. So even with an awful guess, we can still move to the answer.
So if the answer is negative.
It doesn't matter.
What if it's not 1 the actual value? It could be like 3, 4. That the calculator will say 3.
We usually round our answer to 3 significant figures.
No. Like now it's just giving you 1, 1, 1.
Yeah, staying at 1. Yeah.
Because the answer is 1, that's
Mhm.
why it's giving 1.
Oh, I see what you mean. Usually what happens with the calculator is it ends up fixing at a limit because it has to round off. So even if the answer was something weird like 1.3216, in other words, my point is eventually your calculator will stop changing its value because it has to round the answer off. Okay, so Newton-Raphson method, it works, but there are advantages and disadvantages. So, an advantage of the Newton-Raphson method is it's easy to calculate. Okay. Another advantage is quite quick. You know, it's pretty fast. And disadvantages, well, one disadvantage is that it only gives you one root, even though the answer might have more than one root.
So you can do one.
Yeah. The second disadvantage is it doesn't always work. So it will fail if it hits a point where the derivative is equal to 0. Because in the formula for Newton-Raphson, you have to divide by the derivative. So if you hit a derivative equals 0, then it'll fail. Yeah.
Sometimes you can't use it for linear.
Yeah, you couldn't use this for linear. Well, the derivative there is 1. Yes?
Will it ever pass the actual value?
Yeah, this is the other thing. Another problem with it is it could get stuck in a cycle. So it could end up getting stuck and not being able to move. Yeah.
So why we use?
But these are only special cases. For 99% of our problems, it'll be quick and easy to use, and it's certainly better than just blindly guessing. But
We never pass in, for example, the answer is 2, the root is 2. So we never go like 1 point something.
no, once it gets close to the root, it will fall into it. But another, not a disadvantage maybe, but another note, of course, is before you use Newton-Raphson to find a root, you need to know if there is a root. There's no point in trying to find a root if there isn't a root. So does anyone know a way to check if a function has a root? So you want to check if this has a root between, let's say, A and B.
Discriminant.
But if it's a cubic, it has no discriminant.
Sure.
That's okay. Think about the graph. So if it has a root between A and B, it means it looks something like this. So it means that if f of A is negative and f of B is positive, it must have crossed the axis to go from a negative to a positive, so therefore it has a root. Let me give you an example with the one we just did. Here, what is, or maybe not that one because that's actually not a good example. Let's go to the side, wait one moment, let's go to the side. Let's say I have something like a function like this, y equals x, oh this is the one I'm doing, right, x squared minus 1. What is f of 0.5? Well, that will equal 0.5 squared minus 1, which is minus 0.75. So at 0.5 we're negative. And what about f of 2? Well, that would be 4 minus 1, which is 3. So when we're at 2, we're positive. So there must be a root between 0.5 and 2. Is there a root between 0.5 and 2? Yes, we just found it. It was 1. Of course, it also works if it goes from a positive to a negative. So if FA is positive and FB is negative, then that's also a root. What about if they're both positive and they're both negative?
Maybe the boundary values, no.
No, if they're, we just don't know. So for example, if they were both positive, it could have gone like this: positive, negative, back to positive. So we would never have known that it passed it twice. Or if they're both positive, maybe it's because it went positive down a little bit and back up. So if they're both positive or both negative, there could be no roots or there could be a million roots. So in the exam, what will happen is they'll always make it so that there is a root. So there should be a positive and a negative. Yeah? Okay, so the next thing to check is how many times do you need to use this formula? Well, it depends on how accurate you want to be, okay? But as a rough guideline, I thought I had it here. Oh yeah. As a rough guideline, the number of times you'll need to use Newton-Raphson's formula should equal log base 2 b minus a times 10 to the power of how many decimal places you want.
What's that?
So this is how many times you need to use the formula. So for example, let me give you an example. Let's go back to our example we were using of x squared minus 1.
Okay.
And we just proved that there's a root somewhere between 0.5 and 2. Because f of 0.5 is negative and f of 2 is positive. How many decimal places would we like? Well, let's say we'd like 2 decimal places in our answer. Then the formula says you need to use the rule this many times. Log base 2. What's b minus a? 1.5 times 10 to the power of, how many decimal places did you want? You wanted 2. So if I type this in on my calculator, let's see what I get. Log base 2, 1.5 times 10 squared. So it says if you want to get it to, well, really we should round it up to 8. If you want to have it, your answer correct, to do that 2 decimal places, you need to use the rule 8 times. And I should also point out, you use the rule
What is 7.1?
7.2.
How does that round into 8?
Because if I use 7, I'll get less than 2 decimal places accuracy. So we use n equals 8, and we start somewhere between a and b. So as long as we start somewhere between 0.5 and 2, and as long as we use the rule 8 times, we'll be accurate to 2 decimal places. Let's test if that's right. Pick any number between 0.5 and 2. And don't say 1, because that's the answer.
0.45.
I'll try that again after I take some coffee, so just think about your answer, what you did wrong.
It's between 0.5 and 2. 0.55.
Thank you. So let's start at 0.55. You said 0.45. Fine. No, 5.4. Fine. So, let's start at...
It was 9? No.
I said...
Yeah.
So you said start at
0.55.
0.54, we'll say. So Newton's rule says xn plus 1 equals xn minus, what was our formula? Xn squared minus 1 over 2xn. F over f derivative. So I'll use the formula 8 times, and I'll tell you what I get. 0.54 is where we start. So the next value would be that minus fraction squared minus 1 over twice that. So x2, x3, x4. So let me just show you where I'm at now. At x4 I get this. x5 is this. That's x5. x6 is 1. So x7 will be 1 and x8 will be 1.
So I get
So what's happened here is I got 1 at the end. Is this accurate to 2 places of decimal?
no.
Yes.
Yes. Not only is it accurate to 2 places of decimal, it's exactly the right answer. But I would have accepted answers 1.004. That is still accurate to 2 places of decimal, because if I round this off to 2 places, what do I get? 1.00, which is 1. So not only was it accurate, it got me to the answer. Now, please listen. This formula is if you want to be at least this accurate. But often what will happen is your answer will be more accurate than this. So if you want to be at least 2 decimal places accurate in your estimated answer, here you would have to use Newton-Raphson 8 times. But as you just saw, not only was it 2 places accurate, it was completely perfectly accurate. In the exam, they don't expect you to know this formula. But I wanted to show it to you because I wanted you to know a way to know when to stop, how accurate you want to be. In the exam, the maximum they'll ever make you do is this. 3 times. Okay, this is the maximum.
Mostly they just put, like minus 1, minus 2, 2, 3, max. And I was thinking like...
Yeah, but no, but using this formula. So let me show you something here. Right, we'll finish with this example, but I want you to do it first. I'm going to pick a cubic. A cubic. And let me pick a ugly cubic. So let's say this one, 2x cubed plus x squared plus x plus 1. I want you to use Newton-Raphson's formula. I know what, I'll just do it. I'll show you some examples because I haven't done many examples. Okay, so the first piece of business... I know, I'll do it. The first piece of business is you want to know that there's a root. So let's try some number like minus 2. If I put minus 2 in here, I know what is going to happen. Will I get a positive or negative number? I already know in my head from looking at it it'll be negative because this will be minus 2, 4, this will be minus 16. Minus 16 plus 4 minus 2 plus 1, it's definitely a negative number. And if I put in f of 2, what will happen? Will I get a positive or a negative number? I get a positive. So therefore, there's a root somewhere between minus 2 and 2. Newton's Raphson formula says xn plus 1 equals xn minus. So what do I put on the top?
In the exam, they give us the...
They will. And what goes on the bottom? The derivative.
Yeah.
What's the derivative? 8? Sorry.
This is the formula for cubic.
No, it's Newton-Raphson formula again. It's for anything. 6 xn plus squared plus 2 xn plus 1. Now, pick a number between minus 2 and 2. Any number you want. 1. Okay, I want everybody to type 1 into this formula and tell me what they get as the second value. I got 4 over 9. Now, after I use this formula, say, for example, on my calculator, I'll use it 10 times. After the 10th usage of the formula, I'll get this. So I'll just round this off. I'll say the root, I think, is roughly minus 0.73, we'll say 9. The 3 significant figures.
I think it's 4 over 9.
Well, then you typed it in wrong.
I got 4 over 9.
You got 4 over 9.
The other one is minus.
Okay, I got 4.
No, I jumped to 10.
10 max.
Okay, listen. Listen.
Yeah.
Listen, look up, put the calculator down. Calculator down. Put it down. So I used this formula 10 times. I didn't even need to use it 10 times. 3 times is enough. So after 10 times of using the formula, I got to this number. And to 3 significant figures, that's this number. Do you know how to use your calculator to get the roots using cubic?
No.
You do. Mode 54.
Yeah.
So see what mode 54 says the answer is. You ain't got no mode 54 on that thing.
Yeah, stop it.
Yeah, but use mode 54.
Most of the and what should I put?
The cubic. See what the roots are, the cubic. Here's the cubic, it was in the question at the start.
2x.
Yeah.
What's the first root?
It's 0 point.
It's this.
Minus.
Yes.
Your calculator is using Newton-Raphson to get the root. There's not a little person in the calculator working out the answer. There must be some process. So what your calculator does is it uses Newton-Raphson 1,000 times to get to the root. Now you notice this because when you type it in, watch, if I type it in here, mode 54, 2, 1, 1, 1, and if I press equals, listen, calculating, stop.
Yeah.
It took a while to calculate because it did the formula 10,000 times to be super accurate.
False.
Why doesn't
Each single time is
why
false.
doesn't it take its time?
No, you don't have mode 54 on that calculator.
Oh yeah.
Why doesn't it take its time for 2 plus 2?
For what?
Quadratic, no, the.
Just do
2 plus 2 equals. It didn't take any time.
Yeah. You have it.
Why did it take time?
2 plus 2? Because it only has to do one thing. Whereas here it has to do 10,000 things. No, leave it. I told you this is the best calculator to use for the class.
Who's on?
I only see one of these. This question,
You can buy this from Eaton.
How
But
much?
Eaton is for 30.
Yes, exactly. It's expensive.
But you can buy online for
Listen.
50. Yeah.
This is a very common exam question in both section A and B. And it's a very important topic in modern engineering because it relates to computers. Because you can imagine programming a computer to do this repetitive process 10,000 times. Okay, so it's related to computer science, it's related to programming, it's related to engineering and calculus, it's a maths and physics topic, and it's related to your assignment. So numerical methods is super important for you engineers, regardless if you're doing engineering, physics, computer science, or whatever.
In the exam?
And it's important in the exam. So in other words, it's important in your life. Alright, so you want to try, 1 or 2 from each. Right, let's get out of here.